The death of the block bottleneck. MegaETH is processing 100,000 transactions per second by treating the blockchain state like a live video stream rather than a series of heavy snapshots. This throughput is possible because they have decoupled execution from state synchronization using a technique called differential state updates. Instead of sending the entire modified state to the network, the sequencer only broadcasts the specific changes or deltas generated by each transaction. This shift moves the performance bottleneck from the slow disk speed of individual nodes to the actual capacity of the network wire. This massive increase in bandwidth efficiency is the engineering foundation for what the protocol calls real-time responsiveness. This mechanism allows the network to maintain high fidelity without forcing every node to reprocess the same redundant data. This efficiency directly impacts how quickly the global state can reach consistency across diverse geographies. Syncing through deltas, not snapshot. In traditional Ethereum-style architectures, full nodes spend a significant portion of their compute cycle recalculating the entire state trie after every block, just to stay in sync with the head of the chain. MegaETH bypasses this cycle by having the sequencer compute the state diffs and push them directly to a set of specialized full nodes. Think of it like a cloud-based document editor that only syncs the specific letters you typed, instead of requiring every collaborator to re-download the entire 10,000-page file every second. This allows nodes to update their in-memory state in microseconds without touching slow hard drives during the critical execution path. By eliminating the input-output overhead of disk access, the protocol achieves a latency profile that matches traditional centralized databases. But this reliance on high-performance diff streaming creates a specific trade-off in network topology and hardware requirements. The reality of specialized nodes. To maintain this real-time speed, the MegaETH sequencer requires massive amounts of RAM to keep the entire state accessible in memory, effectively avoiding the millisecond delays of solid-state drives. While critics argue this requirement leads to centralization, the architecture deliberately separates the role of execution from the role of verification. High-end hardware is mandatory for the sequencer, but the differential updates allow even lower-spec nodes to keep up with the firehose because they are only applying pre-computed patches. This design creates a tiered system of specialized infrastructure that prioritizes raw performance over the traditional ideal of node equality. This is an engineering bet that the future of on-chain activity requires high-frequency execution environments that cannot be sustained on consumer-grade laptops. This specialized structure effectively shifts the focus toward how we define decentralization for high-frequency applications. The shift toward continuous state streaming. The transition toward differential state updates represents a fundamental departure from the legacy model of discrete block settlement. By prioritizing in-memory execution and specialized node tiers as seen in the previous sections, the protocol has essentially converted the blockchain into a high-bandwidth data stream. This shift transforms the state from a static ledger that nodes must reconstruct into a live feed that they simply consume. For the application builder, this removes the ceiling on compute-heavy logic, effectively ending the era where gas optimization was the primary engineering constraint. We are moving toward a world where on-chain logic can be as complex as traditional server-side code without the latency penalty. However, the real signal under the noise is that this architecture shifts the burden of trust from the hardware to the zero-knowledge proofs or fraud proofs that ensure these fast sequencers remain honest. The next major indicator to watch is the network performance during sustained high-load congestion, where bandwidth saturation between the sequencer and the full nodes will finally reveal the physical limits of this streaming architecture. Subscribe for more.